Hello, I welcome you all to this another interesting screencast. The problem reads that linkage is subjected to a force of P equal to 2 kilonewtons. Determine the angle theta for equilibrium. The spring is unstretched when theta is equal to 0 degrees. Neglect the mass of the links. This problem is coming from the Engineering Mechanics Statics textbook by R.C. Hibbeler. So we are going to attempt, or we are going to solve this particular problem by using the virtual work method. This is an alternative method to the equilibrium of a particle, to the equilibrium of rigid bodies, to the equilibrium of interconnected rigid bodies. Again, I repeat, is an alternative. Therefore, it means we are able to solve this particular problem with the methods of equilibrium of rigid bodies or interconnected rigid bodies. So what is virtual work method? Virtual work method states that the total virtual work in a system is equal to 0. Del U is equal to 0. Okay, and this is due to virtual work from the forces. Okay, this is due to virtual work due to forces and virtual translational displacement is also due to couple moment and rotational virtual displacement. And when we sum up the work done by forces as well as couple moments in a system is equal to 0. So the force itself is supposed to be collinear with the translational virtual displacement, and the work done is classified as positive. Otherwise, it is negative. The couple moment also is supposed to be collinear with the virtual rotational displacement del theta, and this is classified positive, otherwise it is negative. So basically this is what virtual work is, and we want to use this particular method on this particular problem, which again you can solve using the equations of equilibrium for static bodies. Okay, right. So first things first, when we are using this particular method, we are supposed to draw the free body diagram and the free body diagram of a deflected or displaced structure. Okay, and we need to maintain as we draw that, we need to ensure that the movements at all the joints are taken care of, as in the configuration of the system itself does not change. Okay, all right, so let's draw the free body diagram first. So we draw the free body diagram. So here we expect a reaction force in that manner. This is a hinge, and also there like so, and there also we expect a reaction force like so. And then here we are going to let's say we cut this particular spring there, so we are going to have some tension or some spring force like so in that direction, and there in that direction like so. So let's label this. So let's call this as Fs, spring force Fs. Then let's call this here as our Ay, this one as Ax, this one as Dy, this one as Dx. Alright, what else? This is about it, right? So now let's draw the deflected or displaced configuration of this particular system. So we need to first apply some virtual displacement. This virtual displacement can be applied at any of these joints. We can apply it at A. Okay, at A we can apply a rotational virtual displacement. At B we can apply a translational at C, a translational at D, a rotational. So we can apply it at any point. It doesn't really matter where you apply it. Okay, the solution comes out the same regardless of where you apply the displacement. After you've applied displacement, then you draw the displaced or deflected configuration of that particular system. All right, so I'm going to apply it at C. So I'm going to apply it in the direction of my force. Again, you don't have to do that. You can apply it anywhere else. So apply it in this direction like so. So I have applied some virtual displacement in that manner like that. All right. So let's say this is my my displacement. There we go. Okay. So it means the configuration of the system will be something like this. I'll have something like this. Okay, and then something like that. Something like that. Okay. Right. And then something like that. Okay. So let's say we're going to have a configuration like that. I may have exaggerated it a little bit, but something like that. Okay. So I'm going to call this movement downwards there as this movement here as my del y c. Okay, so we are going to have two movements here, right? We have this movement. We are also having a movement in this direction. All right, there's also a movement in this direction, right? All right, in that direction like so. Of course, you can call this one here, though we are not going to have any work in that direction because we don't have any force. This one you can call it del xc. Okay, and then here at this particular point here, we are going to also have some movements. We'll have downwards here. We'll have a movement, a downward movement also at B, like so. We're going to have a downward movement like so. Okay, as well as horizontal movement like so. Okay, so we'll have these two movements here. So this one we are going to call it, this one we'll call it this is del xb. Okay, and then this one we'll call it, this is del yb. Okay, where else? Of course, at A there is just a rotational displacement, but we don't have any couple moment there. Okay, so we have all those displacements there. Of course, we also have a movement there like so, a rotation and so on. Okay, call it del theta a, the other one del theta d. Okay, all right, but we don't have any moment there, so we don't expect any virtual work. So we only have virtual work where we have a force and a displacement and they are supposed to be collinear. Okay, that's when we have a virtual work. Great. So our system is done and we've been told to neglect the mass of the links, right? So we have been asked here to find theta, but we have this spring force that we need to define. Okay, so we've been told that at theta, so spring force, we know that spring force is equal to the the spring constant itself times the change in the stretch, okay? And K itself is given as 15 kilonewtons per meter, right? And S is going to be equal to L final minus L naught, okay? And we know that L naught is equal to what? 0. 0 what? Is equal to 0 meters at theta equal to 0 degrees. Okay, what about L final? L final, we can calculate it. Let me just show it right away. So L final is going to be equal to, from there to there, this is the stretch, right? It is the stretch, so there we go. This is the stretch. Great. This is the stretch. So this one is equal to, this one is going to be equal to, we have this angle here. So this becomes x. This becomes, we are going to call this as our x. Let me write the actual. So the length of the spring, the length of the member. What is the length of this member? This is 0.06. 0.06. And then we have the angle there. So this side, it is cos, therefore this is going to be 0.6 sine theta. So that is the stretch. That is the final length. So L final is equal to 0.6 sine theta. Okay. That is the stretch, the final length of the spring. Therefore, the spring force is going to be equal to 15 by L final, which is just equal to 0.6 sine theta minus 0. So this just becomes like this, and then we multiply this 15 by 0.6. This gives us a 9 sine theta, right? So that is our Fs. So now let's define our reference point. Our reference point, therefore, our reference fixed point is, we are going to choose A. Okay, you can even choose D. We are going to choose A for us. So now let's define now the equations that defines the positions of our displacement. So this one here, it is from this point, from AY to B, from there to there. Okay, this is one. Okay, and then the other one, it is from there. This is from here to A. So A will just be drawn from there like so, since we don't have space the other side. This is from A. Okay, all right. So those are the coordinates. Okay, so this is defining the position of our displacement with respect to A. So we are going to call this one as xb. Okay, it's in the x direction. Okay, and then this one we are going to call it yc. It is in the y direction. All right, so let's define them. So we are going to say xb is equal to Let's look at the position of of B. So this one is going to be equal to 0. This is 0.6 sine theta. All right. So now let's write the vector displacement. We'll say del xb is equal to 0.6 cos theta del theta. All right. The other one is yc is equal to this one. Yc is equal to 0.6 cos theta. Therefore, del yc is just going to be equal to minus 0.6 sine theta del theta, and I'm going to put it, I want the absolute value, so this just gives us sine theta del theta. All right, so we have these two equations and we have the spring force already. So what we just need now is the virtual work equation, so that we plug in all these particular virtual displacement with their respective forces. Okay, so we know to say del u is supposed to be equal to 0. Therefore, we are going to say we have, let's start with the points where we have active forces. At A, we don't have any translation of forces in the X or in the Y, so no work. We don't have any couple moment there, but we have a rotation of virtual displacement, so no work. At B, we only have work in the horizontal direction, no work in the vertical at B. So and the work here, if you look at the work, is going to be negative because the spring direction is in the opposite direction with our virtual displacement. So we'll have a negative Fs del xb. Okay, and then at C, we only have work in the vertical direction because we have a force and a displacement. In the horizontal, we don't have any force, but we have a virtual displacement. So, and the force in the vertical direction is in the same direction with the virtual displacement. Therefore, we're going to have a positive virtual work. So we'll have plus P, then del YC. Where else? At D, we don't have any translation of virtual displacements, okay, and we don't have any couple moment there. Therefore, the virtual work there is going to be 0 at D. So we only have 2 points, okay, that we are concerned about. So this is going to be equal to 0. So now we are going to plug in all the values of Fs. Fs, we know what it is. We calculated it is 9s. So we'll say replacing the Fs there. Fs is 9 sine theta, 9 sine theta, okay, times del xb. What is del xb? We said is 0.6, okay, cos theta, del theta outside there, then plus, we have a p there, then del yc, it is a 0.6 sine theta del theta equal to 0. So if we factor out del theta, then we'll have what is 9 by 0.6. So we have a minus 5.4 sine theta cos theta plus 0.6 p sine theta equal to 0. And we know that del theta is not equal to 0. Okay, therefore the only part that will be equal to 0 is this part here. Okay, right, so So what we need to do now is to solve this particular equation. Like we said, the only part that is going to be equal to 0 is just this part alone, like the earlier on said. So we can divide through by sign, we can get rid of it, right? And then what we remain with there is just a minus 5.4 cos theta plus 0.6p equal to 0, right? So we can make cos theta subject of the formula. This is going to be equal to 0.6p divided by 5.4, and P is equal to 2 kilonewtons is given. Therefore, making theta subject to the formula, this will just give us, grab your calculator, replace 2 in there, so we have 0.6 by 2 divided by 5.4. Cos inverse of that, we have a 77.16 degrees. All right, so this is the final solution. This is the angle required for equilibrium. All right, I hope this video was helpful, and if it was, give me a thumbs up, like my video, continue subscribing and liking my channel. Bye bye, and see you in my next screencast.